So please.
Hello, can you hear me?
Yes.
Yeah. So, okay, thanks. First, I would like to thank to organizers for giving me an opportunity to present my work here. In this presentation, I'm going to talk about the precision of relativistic orbits of a particle in the black hole and naked singularity spacetime.
So can you, sorry, can you speak up a little bit?
Okay. So these are my collaborators, and my talk would be based on this work. If you are interested, then you can refer it. See, the outline of the talk are given here. And to begin with the introduction, I will talk about the possible causal structure or space-time geometry to describe the galactic center and its dynamics. Then I will discuss the derivation of the general orbit equation for the spherically symmetric and static spacetime. And using this orbit equation, I will show the periastron precision in the Schwarzschild black hole and Joshi, Malaparina, and Narayan naked singularity spacetime, and then discuss about the nature of the periastron precision in the Kerr and deform Kerr geometries. And at last, I will conclude with the important result of our recent work. So, as we know, the Newtonian mechanics fail to explain accurately the perihelion precision of Mercury. And to explain this phenomena, we need to consider the general theory of relativity. And by the observation, Mercury moves its perihelion forward by 43 arc second per century, and it is very small compared to the precision of stars uh, near the galactic center of the Milky Way. So uh, you can see the recent observation such as the Event Horizon Telescope, Gravity, SINFONI, and UCLA Galactic Center group have been focusing increasingly on the investigating the nature of the galactic center, and there are many S stars which are rotating around uh, the our galactic center, and some of them are very close to the uh, central massive object. Therefore, their orbital precision will tell us about the nature of the space time and causal structure around of the Sagittarius A star. So, as you can see in this figure, S62 is known as the shortest period star. It's around the 9.9 year orbital period, and it is very close to the galactic center. And the astrometric data of the A stars are given in the declination and right ascension. And for more detail, you can refer these papers. So the existence and observation of the shadow uh, is not sufficient.
So question, can you
Yes.
go back to your slide? So
Yeah. So,
SO102 also has gone through the whole period now.
okay.
The orange one, SO102. It's what is the period of SO102?
SO102 is a period of 11.5 or something.
Uh-huh. So the both, I mean, I knew about S2, but so the red and orange ones have full periods
Yeah.
now. Okay.
Yeah. The SO102 is also known as the S55, or its orbital period is around 11.5 years. So the recent observation by this paper gives the all another shortest known period star, and that is the S62.
Yeah. Thank you very much. Thanks.
Yeah. So the as we know, the in April 2019, the Event Horizon Telescope revealed the shadow image of the galactic center of M87, and in near future, it is going to be reveal the shadow image of Milky Way galactic center, and there exists the compact radius of Sagittarius A star, and the existence and the observation of a shadow is not sufficient or need not ensure the existence of an event horizon necessarily in the galactic center. So we need a further and more detailed theoretical as well as observational analysis in order to decide whether the galactic central object is a black hole or a other exotic compact object such as the naked singularity or gray star. So, from the nature of the orbits, one can predict the causal structure of the space-time at the galactic center. So, in general, the outside a massive body, one can consider a vacuum as pressure and density drop almost to zero. And therefore, outside a massive body, we generally consider the Schwarzschild spacetime as an external spacetime, and inside the this massive body, it can't be a Schwarzschild spacetime as pressure and density are not zero inside. So it is a well-known the solution of Einstein equation for the and it is a spherical, symmetric, and homogeneous dust collapse, and it is always terminates into the Schwarzschild black hole, and the metric of the Schwarzschild black hole described by this equation, and where the 2m is the Schwarzschild radius, and the d omega square is the metric of two sphere. So as we know, due to the flat velocity profile of stars in galaxy, we consider an unknown spherically symmetric matter distribution throughout the whole galaxy, and this matter called as a dark matter, or you can consider other matters and others baryonic matter. So it is considered that the galaxy reside inside a dark matter halo, and therefore outside the dark matter halo, one can consider the Schwarzschild space-time. So, however, inside the dark matter halo, density and pressure is not zero. So, therefore, one needs to consider more physically realistic space-time, and that is seeded by dark matter or other baryonic matter, and it is a well-known picture describe the rotation curve of spiral galaxy M33. So now I am going to talk about the one of the solution of the gravitational collapse, and it is the equilibrium state of the gravitational collapse, and the it is known as the Joshi-Malla-Farina-Narayan naked singularity, and it is formed from the gravitational collapse of matter cloud with zero radial pressure and non-zero tangential pressure. So and it is also obtained via the dynamical evolution of a matter cloud, starting with some regular initial data. So the space-time geometry of Joshi-Malla-Farina-Narayan naked singularity described by this equation, and it is a spherically symmetric and static space-time where the m naught and rb are the positive constant, and in physical sense the rb is the radius of the distributed matter halo. So now from the general spherically symmetric and static space-time, one can derive the orbit equation using the timelike geodesic and some conservation laws of energy and angular momentum. So one can derive the orbit equation for the general spherically symmetric and static space-time, which is the second order nonlinear differential equation, and where GTT, GRR, and G55 is a function of R, and 1 over R is equal, we consider the 1 over R is equal to U here. And the function of A of U and B of U and C of U described by these equations. And in this equation, where gamma is the conserved energy per unit rest mass, and the H is the conserved angular momentum per unit rest mass. And all the throughout the whole calculation, we consider the orbital precision in the equatorial plane. So that's why we consider the theta equal to pi by 2. Now, to understand the nature of the orbital precision in the spherically symmetric and static spacetime, I have considered here the Schwarzschild black hole and Joshimala Farina Narayan one naked singularity model as a background spacetime. And you can see here in figure A, it is described the particle orbits in the Schwarzschild black hole, where the dark region shows the position of the black hole, and a brown circle uh, shows the minimum approach of the particle towards the center, and it is called the periastron points or position. So, and in the figure B and C, uh, represent the particle orbits in the J-main naked singularity, and you can see an interesting behavior that emerged is the orbits around the naked singularity allows the negative or opposite precision as compared to the Schwarzschild black hole. Here I mean to say the negative precision is the phenomena in which the angular distance traveled by a particle uh, in between two successive perihelion points will be less than 2 pi. So here in figure A and B, you can see the angular distance traveled by a particle in between two successive perihelion points is greater than 2 pi. So it is known as the positive precision, and it will be uh, shift into the direction of the particle orbit. So here in figure C, it is less than 2 pi. So therefore it is called the negative precision. In other words, if particles orbit will precede or shift in the direction of the particle orbiting direction, then it is known as the positive precision. While for the if particles orbit will precede in the opposite direction of the particles orbiting direction, then it is known as the negative precision. So as you can see, the orbital shift for the positive and negative precision. And the if we consider more physically realistic compact object at the galactic center, then we must consider the rotating compact object. And if we derive orbit equation using the timelike geodesic for the curved spacetime and plot the numerically, we get the periastron precision in the uh, Kerr space-time. And as you can see, the in this figure, it shows the orbits of a test particle in the Kerr space-time, where these red solid lines indicate the particles orbits in the Kerr, Kerr and extreme Kerr black hole, respectively. It depends on the value of the spin parameter. If I consider the spin parameter equal to 1, then it is known as the extreme Kerr black hole. And blue lines considered for the Kerr naked singularity, where the spin parameter exceeds the value of that mass parameters. And here the plots are given for the prograde and retrograde motion of the body. So for that, I consider the spin parameter value in the positive and negative sense. So next, uh, now as we know, it is very much difficult to solve the second order nonlinear differential orbit equation analytically. And by considering the first order eccentricity approximation, one can consider the solution of the differential equation as given here, and where the p and m are real positive constant, and that are used to determine the nature of the orbit's precision. And if the value of the small n is less than 1, then the positive precision occurs. And while for the m, the value of the m is greater than 1, we will get the negative precision. So you can see here in this figure, uh, here one can see the negative precision is not possible in the curved spacetime, as it is not it is not exceed the value of small m greater than 1. Now, if we introduce some parametric deformation due to the electromagnetic radiation by accreting matter around the rotating black hole, then it gives the deformed curve metric, and it is written here as uh, by this metric, and where the rho square and the deformation given by this two equation, where the epsilon is the deformation parameter, and so the curved spacetime has the oblate shape, but however the deformed curved spacetime is more oblate for the deformation parameter is less than 0, and more prolate for the deformation parameter greater than 0. So in this paper, uh, it is stated that the deformation parameter is unconstrained, and however, in other papers, the author discussed the possible maximum value of the deformation parameter is the less than or equal to 19, and that value define some Faraday rotation polarization experiment, and so here we are consider the value of the deformation parameter up to the uh, this range, and one can derive the position of the inner and outer horizon of the deformed curved spacetime by solving this equation. And here in figures, you can see the shape and position of the event horizon. Um, uh, Horizon in deformed curve spacetime for various value of the deformation parameter and spin parameter. So it can be seen that for the value of the deformation parameter equal to 1, and spin parameter equal to 0.8, there exists some directional naked singularity around the equatorial plane, and this uh, 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 directional naked singularity you can see in the 3D view here, and now now, from in this figure, the shaded region shows the existence of naked singularity in deformed curved spacetime, and the area above the blue dashed line in the shaded region is the region where the negative precision is possible, and where the red dots are the solution points for the negative precision, and the remaining unshaded region shows the existence of the deformed curved black hole. And you can also see from this image the deformed curve space time gives the negative precision for the value of the up to the 19 range, and this gives you the negative precision region. And the conclusion of my talk is the observation can give us the essential information about the causal structure of the galactic center and its dynamics. And the interesting difference from our result is that in naked singularity spacetimes, the particle bound orbit can precess in the opposite direction of the particle motion, which is not possible in the black hole spacetime. And the stars can have the negative precision if the naked singularity exists at the center of our galaxy. On the other hand, if stars show the positive precision, then black hole or naked singularity spacetime can describe the spacetime geometry. Uh, Thank you for listening, and if you have any question, you can ask.
Okay, thanks. So questions?
So maybe I will have a question.
Yes,
S2 is supposed to have a orbit precession compatible with Schwarzschild, right? That was a recent paper. Now, of course, it's the
Yes.
numbers are Yeah,
But
I think it's very early to be able to make solid claims like that. And
yeah,
how is it compatible with a Sagittarius A star being Kerr, for example? So do we, if it was not Schwarzschild by Kerr, how much would this precession change? Has anyone looked at that or?
The data of the S2 star is up to the 2019 or 20. Recently, the Gravity collaboration actually published a paper on the Schwarzschild precision, but they take the higher order approximation for the Schwarzschild model, and Schwarzschild black hole always gives the positive precision, and the second orbits of that S2 star also gives the plus or minus error, and that would be also consider in the negative or positive precision. So I mean to say that the data available of the S2 star is not sufficient to distinguish how the next orbit will precede in which direction the next orbit will precede. So it is up in the plus or minus error.
So
Well, I
what,
thought, yeah, go ahead, Lars.
I just wanted to ask, I mean, what is known about the spin of the central object, this Sagittarius A star? Does when this Einstein telescope data or this horizon observation, when that comes around, will that also give some estimate of the rotation?
Pardon me, I can't understand.
Well, I mean, so I mean, it's certainly not a Schwarzschild at Sagittarius A star. If it's a black hole, it's certainly a rotating black hole. But what's the A parameter of that, or what's the angular momentum per mass of that object? Is that known? And will this horizon observation, is it called Einstein telescope, will that give information about the angular momentum per unit mass?
Yes, probably the observation will give the rotation parameter. The existence of the Sagittarius A star at the galactic center. It's of course there must be some rotation. It is not a static, but the slowly rotating object will differ some uh, orbits, and that will that's why I consider uh, the Kerr black hole and deformed Kerr black hole. These are the possibility and the prediction of the orbits, and there are many A star actually. So the if some star can precede in the opposite direction or in the negative direction, then the black hole can not explain this phenomena. So there are the possibility of other orbits at the galactic center.
Okay, so if there are no further questions, so let's thank Parth for this very interesting talk.